All right, here's 2-2, day 2. All things 2s in this lesson. 2-2, day 2. There you go. We got 4 slides. It's kind of a hodgepodge of function stuff, which is a little bit of chapter 2. We're kind of just like not necessarily zoned in on a specific function family, which again, we've really covered lines and quadratics. But really just some of the basic things, not like characteristics of functions that we should know, and then some skills of how to work with them, okay? Some of them are going to be a review, right? You should see a thing or two in here. It's like, yeah, we've talked about that. This is a review of evaluating, and I specifically wanted in there just to get back to function notation, okay, to fill in the table. I'm using this function right here. It's a quadratic, no surprise. That's one of the types of functions we've really worked a lot with this year. But if I were to evaluate, it looks like this. F of -3, it's my x value, just goes in right here. Which would be 9 minus 4. And there we get to our y value. And so these results could be put in a table. Right, so that first entry is saying when x is -3, f of x, which remember is the same thing as y. Right, we could have said here that f of -3 is 5. Doing the same thing with -2. Looks like there you get 0. Right? You could continue this process and fill in the rest of the table, which I'm going to do. Looks like if x is 0, y you get -4. And then if x was 2, looks as though we get 0 again. So if you come across a table, right, this is kind of got 2 different ways to look at it. One, you could be asked to make the table, right, which we just did. Maybe the more likely thing is you see a table of data. You should know that that table is just a list of coordinate points that are solutions for that function, right? Typically, the top row is going to have your x values, and then your bottom row has your y's, and they're paired together as they should be. Okay, the x value right on top of the y. All right, here's a little bit of a new piece. We call this the old piecewise function. Piecewise function is defined by having multiple equations over a specified domain. Usually, if you have a piecewise, you see it right away, and you're like, yep, got it, right? The specified domain will always come with it. Okay, so if x is negative, I'm looking at the top one, you would put that x value into that quadratic. If x is 0 or positive, you would put it into that line. It just kind of feels weird, okay? But when would that happen? Let's say you're looking at data over an interval of time that has a distinct change in its pattern, okay? Like it's starting like right here down at the vertex, and it's doing like a quadratic thing, right? Kind of looks like half the parabola. And then it gets to a certain time and it just changes and turns linear, okay? Data will do that, right? And we may have a really, really funky change in the data, and we're like, hey, let's find a function that really fits it well, and we don't have one, right? That's when a piecewise function would come up and be like, okay, up until like right here, it looks very quadratic-ish, and then it changes to a line. So then just use the different intervals and use 2 separate functions. You just got to be careful on which one to put it in. if x is -3, I plug it into the quadratic, okay? Piecewise functions sometimes look worse than they are. They're typically not that bad. You got to know when you have an x value, you're only putting it into one of those functions. You just got to figure out which one it is. If f was 0, I put it in the bottom one, as it says right here. If x is greater than or equal to 0, here's 6, that's positive. All positive x values are going into that line. Okay? All right, let's find some zeros. This is just straight review. I know we've talked about it a lot. It's a big thing. I mean, it's a really, really huge thing with quadratics, okay? It can be for other functions, so I've got a couple examples here, one with a quadratic, one that's a line. Right, if you're ever asked to do it, you set the function equal to 0, because that's like your y value, and then you're asking yourself the question, what x value gives me a y value of 0? So I set it equal to 0, subtract 10. Divide by -2. And get my solution of 5. You would typically expect when you're finding zeros with lines, you're going to get 1. Quadratics, that's not the case. You could get multiple. Could get 2. Wouldn't be surprised if I do. A line's never going to give you 2. Oh, 2 factors of 6 that add up to -5. I do believe -3 and -2 will do the job. X minus 3. Okay, add 3. Again, you might be wondering why we're doing these, because you feel like, I mean, we've talked about finding zeros. We've done it. I wanted to talk about these two. By the way, you get 2 and 3 as your two solutions. Side by side. Because sometimes if you know what you're supposed to do to find a 0, but you kind of get messed up in doing it because of the function type, right? In other words, the steps that I used to solve for a line, they weren't the same as the quadratic, right? Sometimes you see some really funny things, particularly if I ask you to find the zeros of a line. You see some really weird things like trying to apply the quadratic formula, trying to factor, okay? First things first is to recognize what type of function do I have. If it's a line, it typically will take me 2 steps of solving to get my 0. I'm not going to factor. I'm not going to use the quadratic formula because it's not a quadratic. It's just a line. Quadratics are handled very differently, right? They're not a linear function. They have different approaches to find those zeros. There we would, worst case, use our quadratic formula or factor, okay? Factoring tends to be the quickest way to go. Recognize which one you have is kind of my point. Okay, in particular, if it's a line, keep it simple, recognize it for what it is and just solve it. All right, so this is also a little bit new, sort of. Finding where 2 functions equal each other. You might be thinking, hey, wait a minute, we already done this? We've done it with lines, okay? We've done it to find where 2 lines intersect. We have not done it with quadratics. Here's how it works. First things first, set the two equal to each other. We are going to solve x squared plus 1 equals 3x minus x squared. Now that one's kind of written in a funny order, but don't be fooled, right? It has a highest power of 2, so it's a quadratic. And we got to find whatever x values make that true. Okay? We're solving a quadratic. Okay? Take the same approach we always do. We don't like solving quadratics in any sense at all if they're not set equal to 0. Okay? So we're going to take ours, get it set equal to 0. Once we have that, we would take the approach that we would solve it like any other quadratic. So we have 2x squared plus 1. I'm moving everything over to the left. Okay. We have a quadratic. We got to find zeros. Okay? Just like any other, right? This part of moving everything to the left is really the only new part. This one's factorable. I put a -1 there and a -1 there. Think about the outer and the inner, right? If I were to FOIL those, that would be -2x and another -x. That would get me to -3, which means I can solve these two factors separately. And I get x equals 1/2 and x equals 1. Okay? There's a lot going on there, no doubt about it, right? But again, split it up into two different parts, right? Really, the cutoff is right here, right? Everything from there on down is like solving like every other quadratic, right? If we want to find the two solutions to a quadratic, we got to rearrange our parts so that it equals 0. If we're solving one quadratic equal to another, no exception, right? That's those are the points we got to find. Let's do one more. X squared minus 1 equals -x squared plus x plus 2. Okay? I'm going to take the same approach, everything over to the left. Everything over. And I'll just go in order. I'll do my squared terms first, then my x terms, then my constants. Should be able to do it in 3 parts. 2x squared minus 1 equals x plus 2. Then you could take away x. There's no like terms over here for x, so we just add it in the middle. 2x squared minus 1 equals 2. Then get our constant. 2x squared minus x minus 3. Okay. That's all kind of just getting it ready to solve, right? We're taking kind of a new and different problem with quadratics and turning it into one that we've done before, right? That's the way we got to do it. Whatever, it doesn't matter the context of the problem or exactly what's going on. If it's under kind of the general direction of solving a quadratic, it's got to be set equal to 0. If you were looking at this, once you had it set equal to 0 and said, I'm going quadratic formula, you can, okay? I'm just giving you more examples of factoring. I'm not going to rework these with the quadratic formula, but be my guest to do it that way. If you do it correctly, you'll get the same 2 answers. All right, need factors of -3, I believe, +1, and -3 will do the trick. And now I can solve these. Again, with the quadratic, I am expecting two answers. I got -1 for my first, and it looks like I will get 1.5 or 3/2 for the second. Okay, there you have it. You got two good examples of how to solve a quadratic equal to another quadratic. That's all for section 2. Little preview for section 3. We kind of get back to the topic of domain and range, especially domain. We talked both. Graphs. Graphs are going to show up, but let me give you a little disclaimer. It's not going to be all graphs all the time. There's going to be a bunch, not a ton. The primary focus in section 3 will be on reading graphs, not making them, right? That'll be a little bit of a shift. We spent a lot of time so far this year on constructing graphs ourselves. That's fine. That's a good thing to be able to do. Reading a graph that's just presented to you, just as important. So we'll be doing a lot of that in section 3.